1309 заседание гидродинамического семинара. Докладчик профессор Бейсенс из Парижа, из Высшей школы технической физики и химии, знаменитой школы Парижа, в которой работали и получили свои Нобелевские премии Пьер и Мари Кюри, и Рене Фредерик Кюри, который долгое время был директором Ланжевен, затем был директором Держен, Шарпак, еще там Нобелевский тоже лауреат по химии. То есть это, в общем, самая знаменитая, пожалуй, школа Парижа, которая поэтому и называется Высшая школа технической физики и химии города Парижа. Профессор Бейсенс знаменитый ученый, выдающийся ученый в области исследования поведения околокритических сред, то есть жидкости вблизи термодинамической критической точки, жидкость пар. Сегодня он, значит, вообще он будет у нас читать 4 лекции. Сегодня лекция, она не по околокритическим жидкостям, название вы видите. Он работал в этой области тоже. Сегодня он нам об этих результатах расскажет. А завтра у нас семинар сдвоенный, 2 темы. Одна из которых это пистон-эффект, это поршневой эффект в околокритических жидкостях, эффект в категоризационных жидкостях. И вторая тема – это тема вибрационная конвекция в таких же околокритических жидкостях в условиях пониженной ферментации. Ну и, наконец, это завтра в 3:15 в этой же аудитории, а послезавтра тоже в 3:15, но а что делать? Ну, уже в пятницу. А послезавтра в 3:15 в аудитории 202N в корпусе лекция, которая называется «Структура возникающая при образовании росы, изморози и закрывания физика и химия этих явлений». Вот такой цикл лекций у нас идет. Значит, лекции будут, сегодняшняя лекция будет произноситься на английском языке, вообще все остальные тоже. Если что-то непонятно, пожалуйста, задавайте вопросы на русском языке. Мы переведем на английский или на французский язык. Вот здесь еще один наш гость. Это Ирина Бейсенс. Если мы не справимся сами, то она нам поможет. Вопросы можете задавать или на английском, или на русском языке.
Спасибо. So, здравствуйте. C'est bon? Non. Здравствуйте.
Bonjour.
I don't speak Russian yet. English is not my native language, not yours, I guess.
It's better.
Yeah. So I will speak slowly, but that's the usual way I speak English. And so Tatiana asked me to make a series of 3 lectures. They look different, but they are not so different in the sense that they are all related to phase transition. So here that's phase transition in binary liquids and wetting transition associated to the critical point of this liquid-liquid mixture, miscible liquids, and the stability of colloids. The second lecture will be related to the fact that gas-liquid system becomes very compressible near the critical point. So new way to thermalize the system and also to transport heat can be observed, and especially when gravity effects are absent, that is in space. And the third lecture will be devoted to the condensation on surfaces, this phase transition on the surfaces. So in a sense, that's a lecture of what I will speak about today, with webbing on the surface, and what I will tell tomorrow. So I'm sorry to give so many lectures in such a small amount of time. That's a lot of work for me too, but I think it will be a pleasure. Especially Tanya told me that I could speak for hours, so that's okay. But I won't. So this is the first series of lecture, and this is something which is an important problem for industry, that the cosmetics. You know, if you buy Christian Dior and cream, and you have in the cream you have colloids, that is small particles, and that's very important that the colloids don't aggregate. If they aggregate, you cannot use them anymore. That's old cream, you know, the cream that's oil on one side and something sticky on the other side, and that's finished. So here, that's something we have discovered maybe 25 years ago, and that the stability of colloids can be related to universality, to universal behavior. And that's something important too, because, you know, colloids, proteins are colloids also, and if you want to separate colloids, that's also something that you can use also. And especially this miscible liquid, partially miscible, they have their critical point at the ambient temperature, that is 20 Celsius or 37 Celsius, that's the body temperature, and so that's biosystem can be used. So just to tell that I'm the director of a joint laboratory that I created, which is the SM Laboratory of Supercritical Fluids for Environment, Materials and Space, and that's between the CEA, Commissariat d'Énergie Atomique in Grenoble, ESPCI, I think you know what is this famous ESPCI Paris, and the CNRS in Bordeaux, that is the chemistry of condensed matter in Bordeaux.
École.
You can enter me when you want. Okay, so I will just make, I think everybody knows what critical point phenomena is here, Tanya?
Yes.
So I could go a little bit faster. Just to tell what is a critical point, you know that the first critical point has been perhaps not observed but documented. That's from the Baron, who was an aristocrat, Charles Cagnard de la Tour in 1821. He was performing experiment in a sealed gun. You understand why he was using a gun? Because of the pressure, and sealed with CO2. And in order to know whether it has liquid or gas, he was shaking, not shaking, the CO2 and hearing the splashing. And when he discovered with surprise that above 31 degrees Celsius, he couldn't hear any splashing. He said, oh, there is a leak. No, there was no leak. Just the fluid was not a liquid and vapor, but it became a supercritical fluid that is gas with the density of a liquid. And that's very interesting. We'll see for the application. Of course, after the study was by Andrews and Van der Waals, and that this is a phase diagram that you know, that's the pressure temperature phase diagram, that's solid, the gas, the liquid, and the travel point. And you know that the saturation line ends by a point, that is the critical point. And on this line, you have equilibrium between the vapor phase and the gas or vapor phase and the liquid phase. Above you have the liquid, below you have the gas. And here you have this supercritical fluid, which is a gas with a density of a liquid. So this is a more complex phase diagram where you have the pressure and temperature, that's this phase diagram, but with the volume, and although you see the Clapeyron curve, and with this in pressure volume, the coexistence curve. That we will use. And that there is a fundamental interest for to work near the critical point because you can express all the properties in terms of university classes. And for example, the gas liquid and the liquid mixture, they are Ising-like systems, magnets. And the university class is defined by the space dimensionality D and the symmetry index N of the other parameter. For instance, for the gas liquid, the other parameter is the density, and that's a scalar. But if you look at the lambda transition with helium, that's a vector. So N is equal to 2. Now, there are strong anomalies near the critical point, very large compressibility, critical slowing down, that is, the heat transfer becomes slower and slower for the gas liquid system. And that's very paradoxical because, you know, the heat diffusivity, the ratio of the heat conductivity and the specific heat, and both are diverging. But the ratio goes to 0. Now you have also the industry. There is a very strong industrial interest for CO2. CO2 becomes a good and clean solvent above the critical point. It is as good as benzene. Benzene is very toxic, but not CO2. Also water. Supercritical water, that's a host of very efficient chemical reaction. You can burn at low temperature, that is 500 Celsius, ammunition, for instance, or recycle toxic waste, like waste used in nuclear plants. That's what we are doing. And also for CO2, I forget the storage of CO2. The storage of CO2, that's in the supercritical condition, because that's at a strong depth. So there are other interests for space. We understand that space, in space, the problem is that you have an interface between gas and liquid. So when there is no more gravity, you don't know really where is the gas, where is the liquid. If you use a gas which has a density of liquid, everything is okay. So if you have a density large enough here, when you are opening the tap, the density is decreasing, and so you are going directly from the supercritical fluids to the gas without crossing this saturation line. Also the energy, if you have thermal plants, you want to make electricity, the higher the temperature, the better the yield, the Carnot cycle, you know. And so if you gain only a few percent the Carnot cycle, you gain much more on the cost of the kilowatt per hour. And so there are some thermal plants, especially by Siemens in Germany, that use water in supercritical condition. Also, thermal properties, and that's the piston effect, due to the fact that the system is, that the fluid is very compressible. And so I will tell the story of the piston effect tomorrow. Okay, so now you know what is for the gas liquid system. This is the coexistence curve, temperature, density. This is the magnet description, ferromagnet description. So you have the critical temperature, and the other parameter, M, is rho minus rho C over rho C. So the other parameter, that's the parameter that breaks the symmetry where that's contained the critical point. And for a binary liquid, this will be something related to the concentration of one component versus the concentration of the critical concentration of the other component. Exactly the same. So, to give an idea, for the cyclohexane aniline system, the critical temperature at 1 bar of the atmosphere is 300 K, that's room temperature. But that's easier to study. So there is another, an extra parameter, the binary liquid, an extra field, which is the pressure, external pressure. And so the coexistence curve varies with pressure, and especially the critical temperature varies with pressure. That's something we will use. And usually the variation of TCP can be either positive or negative, and that's between 0.1 and 10 millik per bar. Okay, now you know what is the Landau midfield of free energy. So this, in order to describe the state of the coincidence curve we have seen, we have to describe the energy of the system. So that's the free energy of the system versus the other parameter. Above the critical point, that's temperature here, coincidence curve, the minimum of the energy is 0, but below it has 2 minima. So the energy that describes this system, we can use an expansion, and that's the mean field because it ignores the fluctuation and lambda of free energy. And this expansion, that's critical free energy, the value of the critical point, Fc, plus the integral of the volume of a development versus temperature and other parameter. And because this function should be even in m, because it is symmetrical, and odd in tau, because it varies as tau, this is the simplest expansion with, this is a constant, variation odd in tau, even in m squared to m4. And so this simple description gives you the shape of the coincidence curve by minimizing the free energy versus 2m. Above Tc, that's m equal to 0, and below, that's plus minus, plus, this value, 6 AOP, okay? And tau, the power 1/2. So this is what we call a critical point in the midfield approximation. So now, if you are not at critical, at zero magnetization, so at critical concentration of density, the shape of the free energy is different. And in order to describe this curve, you have to add an extra term, which is the field H by the other parameter. And so I don't give too many details, that the coexistence curve Cx, and that's the free energy. Just to say that you can, with this expression, you can determine the susceptibility of the system. That is the inverse derivative of the curvature. And here you see it from this expression, we have a very simple expression with this exponent -1, that is, the susceptibility of the system diverges when you go near the critical temperature. It goes to infinity. Now, if you consider the vapor-liquid system, gas-liquid systems, if you put m as the density, you get something which is the isothermal compressibility. So the isothermal compressibility of the gas-liquid system diverges near the critical point, and because there is a relationship between these parameters and Cp, this is also Cp, the divergence of the critical point. Very large specific. Now, in terms of binary liquid, that's not the isothermal compressibility, but the osmotic compressibility, nu, that's the chemical potential. And so the osmotic compressibility tends to infinite when you are going near the critical point. Now the specific heat at constant volume, so you can, from this free energy, you define the entropy, which is the derivative versus temperature. And so Cv, that's the second derivative, becomes the second derivative of the free energy. And you see, the second derivative has no temperature or other parameter dependence, so that's a constant for the vapor liquid. In fact, you will see there is a weak temperature dependence. And if you look at the liquid systems, what corresponds to the specific heat at constant volume is the specific heat at constant pressure. So also nearly no divergence. This is vodka, not vodka. I hope so, Tanya.
So cool.
So now there is a problem. Maybe you know. Do you know all this gas critical point story? Okay, anyway, I will go on, because if you know, I'm wasting my time with that. So the problem is now is that you've seen that near the critical point, the susceptibility or the compressibility diverges. In the free energy, we ignore the fluctuations. So this is contradictory. We ignore the fluctuation, and we see that the fluctuation should become larger and larger. So now we will include the fluctuation in the free energy. And in order to and that's also the genius of Landau to have made this expansion. And so the lowest expansion to take into account the fluctuation, that the square of a gradient of the order parameter. So we put the square of the gradient in the free energy, and so now the free energy that's the same as before, and we put this extra term. So, and that's the fluctuation that we have observed in a gas-liquid system near the critical point. We had to go in 0G because you know when you are taking a gas-liquid system near the critical point on Earth, it is so compressible that it becomes compressed under its own weight, and so you are going away from the critical point. So we're going closer and closer. The critical point makes you going further. And so if you look with the microscope in space, this was in the Mir station. We were made, thanks to Russia, we made a lot of experiments from 91 to 99, just at the very end. You can look at this fluctuation there, you see? So this fluctuation, that's density that varies. This is a picture, so it varies in space. And you see that there is some given length scale in the system. And so we will try with this expression of the free energy to get this length scale. So now, in order to solve this equation, we solve this. We don't solve. We consider this equation. We consider the Fourier transform. That is in the Fourier space Q. So we determine the susceptibility. That is the osmotic compressibility, the inverse, and that's easy to write it. You see, this is become a Q square M square. And we found that it varies with temperature at tau -1. There is an amplitude, and this is a variation with Q square, which is 1 plus Q square, psi square. And psi square is related to the susceptibility and varies at the root square of the susceptibility. So now you see that this corresponds to the fluctuation extent, because if you make an inverse Fourier transform of this Q, susceptibility, you get the correlation function of the fluctuation of the other parameter. It's difficult to say, but this is the spatial correlation of the susceptibility, and the inverse, when you invert, you get an exponential divided by R. And psi corresponds to the extent of this fluctuation. Okay? And you see that as it varies with temperature as tau at the -1/2, it goes to infinity. It also becomes larger and larger when you are going towards the critical. Okay, now we have everything in hand to understand the following. So now the problem is, when you are fluctuations, you cannot ignore anymore fluctuations and in the free energy. And so the exponent, that is the temperature variation, of susceptibility, specificity, etc., is not, has to be what we call renormalized. So I won't speak about the Ginsburg, etc., but just to tell that now if you make a proper theory that takes into account this fluctuation, the temperature variation of the number of parameters will be given by power law. So this is the isothermal compressibility for gas liquid, kappa T. That's temperature difference with the exponent gamma. That's the critical isocurve, critical density. And gamma is in the mean field theory was 1. Now that's 1.23. The specific heat at constant volume in the mean field. There is a ghost. didn't vary with temperature. Now it varies with a weak exponent, alpha, which is equal to 0.11. The density of bulk phases, coefficient curve, was delta T at the power 1/2. Note as beta, and beta is equal to 0.325. And that's van der Waals, or midfield, you know, here. The pressure, so I didn't discuss, it was 3, not as 4.8. Correlation function, so I didn't speak. Okay. Correlation length, it is now 0.63, it was 1/2 before. Okay? So that's the renormalized exponent. And you see that the correlation length, that's 1/2. Now that's new 0.63. So now you know everything about critical point. Just there are something interesting and important. There are relationships between exponents. Only two are independent. Only two. And for instance, you can get this relationship, which is very well known. That's what we call the hyperscaling relationship that relates one critical exponent alpha, or two nu and alpha, to the space dimensionality. That's something very interesting to discuss. I don't have the time, but that's very delicate and very clever. And you see that this corresponds to the energy per volume, that is second derivative of Cv, and of the free energy. And this corresponds also to the energy kT. K is the constant, divided by the correlation length volume. And so you get this relationship. And so you have this kind of relationship that is very useful, because if there are only two independent exponents, there are also only two independent amplitude of these scaling laws. This means this is what is called the two-scale factor universality. That is, all the fluids, all the binary liquids, all the systems in this class of universality, if you know only two amplitude, you will get all the other amplitudes. And that's very important, because one of my students, Bruno, is here. He is very tired because he spent a lot of time in the train. And we are making experiment with hydrogen to get the universal amplitude, to get the amplitude of hydrogen. And we are making one single experiment to get two amplitudes and get all the other critical amplitudes for hydrogen. So that's a very important concept. Okay, now we are dealing with we are dealing with binary liquid. Now, from the osmotic compressibility here, we go to the osmotic compressibility. Sorry, Tc over mu here. Instead of specific heat at constant volume, so that's here, we get specific heat at constant pressure, Cp, that diverges a little bit. Instead of the density of the two phases, that's the concentration of the two phases. Instead of the pressure, that's the osmotic pressure. Instead, so now just to show you, this is the kind of scaling law we can get, that the compressibility, that's in log, and by the way, that's Yves Gavrados work, this, in Bordeaux. So that's T minus Tc divided by Tc. And you see that this is the scaling laws that asymptotic, and when you're going further from the critical point, you have what we call the regular behavior, something which, since the fluctuations are becoming smaller and smaller, at the end you will get infield. That is, this exponent will go from 1 to 4 to 1. Okay. And this is for osmotic compressibility for binary liquid. Now this is the specific heat, and that's an experiment which is very delicate that has been done by Johan Straub in Space Lab. That is the divergence of the specific heat at constant volume for the liquid vapor, or constant pressure for liquid liquid. And this has been done in the Space Lab. Okay, now something important, that the critical slowing down. It's okay. So, now we are looking at the transport phenomenon. you have a fluctuation of the order of density, and it will grow, and after some time it will relax. And how will it grow or relaxes? That's by a diffusion process. Maybe I speak too fast, but that's okay? It's okay? Normal? Okay. I cannot go faster anyway. So we have to express this diffusive, how the density, for instance, for gas liquid, the concentration, diffusible. So, for instance, this is the microgravity. This is very a fluid that is SF6. It is very, very close to critical point. You know, that's a veritable tour de force. 10 micro-K, 10 6. So we stabilize very well. And the correlation length is 5 microns, and the typical relaxation time is 1,000 seconds. So this is a movie that I will show you. And perhaps it will work this way. So that's very slow, as you will see. So look, there are some dark and bright parts, and they move. You see, they move very, very, very slowly. For instance, see. So we have at the same time the space and time fluctuation. So you can get the correlation function in space and time. So you see the shape. The shape is fractal, and so this can be explained too, because there is a relationship between the shape of the fluctuation and the critical exponent. Okay. So that's fluctuation in density, so fluctuation in temperature. So what matters? That's the thermal diffusivity, which is equal to the heat conductivity and specific heat. This is density, but which can be considered also as diffusion coefficient KT divided by the shear viscosity and correlation. That's in average. And this diverges as a this goes to 0 at the time at the power of 167. This corresponds to the invert of the correlation length. You remember it was diverging with the exponent nu 0.63, and the phi at the shear viscosity has a weak, very weak critical divergence. So if you have 6.3 and 0.04, it makes 0.67. Okay, now the typical time for the relaxation of the fluctuation, that's, you said, that's the diffusion over the typical length, which is psi. So it is d-1 over psi squared. And so this gives you the typical relaxation time, which varies with this exponent 3 nu, because of that. There is the shear viscosity, so it is roughly as the temperature, T minus Tc at the power minus 2. So this time, that's the critical slowing down. And you will see that this critical slowing down, in a closed container, when you make an experiment, becomes just upside down. It's not critical slowing down, but critical speeding up. That's for tomorrow. And so that's interesting because, you know, in the first experiment we perform in space, we say, oh, how much time do we need to have a sample at uniform temperature if you hit the wall? So CO2, thickness of the cell 2e 1 centimeter, and we are 1 milligauge from Tc. If you make the calculation, it takes 1 month. So really we said, oh my God, it will take 1 month to have the temperature at constant, to have a cell at constant temperature. And when we make the experiment, we observe just upside down. At 1 milligauge from Tc, it was only a fraction of seconds. That's due to the piston effect, but that's another story. Okay, now in liquid-liquid system, so that's the concentration fluctuation, and here that's cyclohexane methanol is nearly gravity compensated because the density of both components are nearly the same. And 1 millikA, but not 10 microcA, 1 millikA, correlation length is 1 microns, but the time is 3 seconds. In fact, what occurs in liquid-liquid, that's the same theory as before, but the viscosity is 30 times larger, so the times will be much, much more larger. The same theory. For instance, in concentration equilibration in cycles of methanol, if you don't stir it, 1 centimeter thickness, 1 millikA, 30 moles. And that's something that everybody that has performed experiment with binary liquid knows. If you take the binary liquid, say, of cyclomethanol, cyclohexaniline, you could say at 1 degrees above Tc, even at 1 degrees, you have to stir it vigorously. If not, you can wait months to have a system that is homogeneous. Okay, so that's only to tell you. Thermalization with liquid-liquid, that's something which is related to lambda and Cp. Lambda has no weak divergence for the system. Cp has a weak divergence. Okay, so the only problem with binary liquid, that's the fact that it homogenizes very slowly. Now, gravity effects. They are very strong on gas-liquid system, but not as strong in liquid-liquid systems, because the density of both liquids can be made closer, and in now in 20 years from now, I think at least, we found a very simple way to have the density of both components very, very finely adjusted. So we consider cyclohexane and methanol. The difference, that's only a few percent. And to make it even better, we make a mixture of cyclohexane and deuterated cyclohexane. We replace the protons by heavy by deuterium, hydrogen by deuterium. And so we can make a very, very finely system. You know, but the problem is that near the critical point, the capillary length goes to 0. And that's a problem. You see, you know what is the capillary length? That's gravity, that's a wall, that's a mixture of two liquids, and due to the capillary forces, if you are wetting or partial wetting, this phase tends to spread over the wall. And so this length on which the meniscus extends gives you the competition between gravity forces and capillary forces. So, so the capillary length, that's the surface tension divided by gravity and difference of density of both phases. But the problem is that the surface tension goes to 0 near the critical point. Why? Because you can express the surface tension as the energy per surface area. The surface tension as a force per length of energy per surface area. Here, the energy that KBTC. The typical surface area, that the square, the correction length. And the C goes to 0. And so, since delta rho goes to 0, this goes to 0, delta rho goes to 0, but the ratio still goes to 0 because of the exponents that are different. So this means when you are going closer and closer, the capillary forces will become too weak to compensate the weight, and you will have always gravity effects with system near the critical point. That's why we are obliged to make fine experiment and to use the universality of scaling in this system to make experiment in zero gravity. That's why we are working together. Okay, now we go to for the summary. Vapor, liquid, same universality class, same behavior. If we replace the density fluctuation for liquid vapor by concentration fluctuation for liquid. Specificity of liquid, no slowing down, no critical slowing down for thermalization. line of critical point with pressure, and you will see we play with it, and strong critical slowing down for the concentration fluctuation due to the viscosity. But enable density matching for composition of Chimie, except very limited. So now that's the story so far, the critical point. I'm just making a break to drink something, and now we go in the core of the lecture, that is colloids and critical points. So if you have some questions about this introduction.
Есть вопрос?
I think something about relation between theory and laboratory experiments.
Oh, there are many. This has been the object of thousands of experiments and thousands of theory. You know that Kenneth Wilson got the Nobel Prize in 1982 for the renormalization group theory. So there was a lot. So now we know. The only remaining problems, that's when you are going very close to the critical point to see whether the scaling theory, there's no breakup. And so now we are working with people from the GPL in the United States. They wanted to make experiments with helium, they cannot do, so now they will use Declic to go very, very close to the critical point to see whether there are not some breaking. So for the time being, there are many experimental results that fits the theory. So that's solid. Okay, so now I go to the colloids. So now the idea is to consider the colloids in liquid systems. So I just go back. So this is the ordinary coincidence curve, concentration, temperature. Now, with the pressure, we have seen that we have a line of critical point. So we have temperature, concentration, and pressure. But there is something else. If you use water, water has hydrogen bondings, and the intermolecular potential between both molecules, the goes upside down with temperature. When you increase in temperature, the hydrogen bonding decreases. So what you get coexistence curves that are upside down with a lower critical point. But now, if you look a little bit further, of course, when you are going still higher, you get an upper critical point. That's usually what you get with water. You get a lower critical point, an upper critical point, and a closed coexistence curve. For instance, 2,6-butadiene plus water. This is at something like 27 degrees Celsius, and this is at 75. 2,6-butadiene is butadiene is dimethylpyridine. So you have also 2,4. So methylpyridine plus water, that's the same kind of thing. Now, if you are putting with water a mixture of water and heavy water, this acts as a field, as a pressure, and you can tune the diameter of the Beysens curve, you see, by changing the ratio of water over heavy water. And so the closed loop can be decreased and even become a point, and that's a double critical point. And even if you look at the temperature, if you make experiment by changing temperature at pressure lower than the double critical point pressure, you get fluctuation because you are close to the critical point, and you don't get any phase separation. Okay? So that's a really good trick if you look carefully. Now I go to the weighting and adsorption. You know what is the difference between weighting and adsorption? So weighting, that's we have two phases, and absorption, that's when we have one phase, only one phase. Okay? So weighting, you have a meniscus, absorption, you don't have any meniscus. So if you have a supercritical fluid, you can speak only about adsorption. Now if you have a two-phase fluid, gas and liquid, or liquid and liquid, below the critical point, you will get wetting. And so this is the wall, this is the fluid, and you know there was a lot of theory of experiments about 20 years ago in order to determine something that John Kahn predicted. That is, when you are going close to the critical point, the contact angle near the wall, the two faces, should go to zero. And that is, you must have complete wetting near the critical point. So this means that this is plotted in the phase diagram, binary liquid or gas liquid, temperature, concentration, critical concentration. At low temperature, you have liquid and vapor. The liquid wets, partially wets the wall with a finite contact angle. Now if you change and go closer to critical point, you should have complete wetting. Okay? I will tell you later why. And now, if you are not at equilibrium between two phases, but you consider a fluid, say, outside the Beysens curve, you should have two regions, one separated by a line, which is called the pre-wetting line, and which ends by a critical point, pre-wetting critical point, where when you are further from this line, you have weak adsorption, and when you are closer, you have strong adsorption. So the pre-wetting line separates two regions between weak adsorption and large adsorption. So this was the story so far. Now if you are going closer to the critical point, you have large fluctuation, so the correlation length of the scale of the phenomenon, the length scale, and what something has been predicted by Fischer and Degen, critical adsorption make a large adsorption on the order of the correlation length side that goes larger and larger near the critical point. So now this is the Kahn argument. You see, it's so simple that I can explain it to you. So this is the wall, liquid vapor, and the finite contact angle. This is the surface tension liquid vapor, the cos theta. It's equal to the difference at equilibrium between surface tension liquid solid and vapor solid. Now you see that it seems logical to assume that this surface tension is proportional to the density of liquid solid and that of vapor solid. So this is proportional to the difference of density between liquid and vapor. And this is in Tc minus T with beta, exponent beta, equal to 0.325. So when you are going closer, this tends to 0. So this means that you should have perfect wetting when going near the critical point. We have to say also that this goes to 0 with another exponent. So cos theta should go to infinity. So that's, did you look at that? This goes to 0 with 0.325, and this goes to 0 to 0.63. So this means cos theta should go to infinity, and you should have complete wetting. But the problem is that here, that's connected not to bulk density, but surface density. And so this exponent should not be the bulk exponent. Also, you have a competition between the van der Waals long-range forces, attraction, with the short-range forces. So this makes the story much more complicated. Okay, much more complicated. That's why after the first story by John Kahn in 1977, there was a lot of development by theorists and a lot of experiments. So this is important because you will see that now we'll see how the force will interact with colloids. Now we have two plates, and that's the two plates. You will have near the critical point a large fluctuation. Some people say that's Casimir effect. You know the Casimir effect due to the quantum fluctuation. That's not exactly so. That's that's critical fluctuation, and I think that people that speak of Casimir, that's an excess of language. But anyway, it's a kind of capillary condensation if you want, and you have a force that will attract the two plates. And so So that's a lot of reference, and some are very. So that the first paper by Fischer and Lejeune was in 78. After that, we performed experiments, and also there is a lot of work by the Siegfried Dietrich group in Germany. They interpret this as a Casimir effect, but I'm thinking, some are thinking that's not exactly so. There was also in Oxford, in UK, the Julia Yeomans group, and they interpret it in terms of liquid bridges. And very recently, in Japan, by Okamoto and Akira Anuki, a very good theorist, they make a new theory with Van der Waals Chaudron. And this is, you see, this is the temperature, this is the concentration, this is the coincidence curve, and they can predict a line of capillary condensation transition that makes forces to press these two planes together. And this should end by a critical point. So that, you know, that's refining the Kahn arguments with taking into account long-range, short-range forces and the new development of what we know about Casimir and what we know about bulk correlation function. Anyway, you see that's, anyway, the experiment that we performed a very long time ago, it was in the last century, in 85, and there is a review here in 94, a more recent review in 98 and 99, and there were also other groups later by Jim Maher in the United States, in Pittsburgh, and Eric Keller dealing rather with biological materials. And that now the idea is to take water, to put colloids, you know that you can stabilize colloids into water, and add another component which is partially miscible, and see whether we can observe by light scattering of colloids this wetting transition. So this was my basic idea a long time ago. It was working, as you will see. So we saw that the colloids, we saw layers of one component growing on the colloids, but at the same time there was forces that make the colloids aggregate, but aggregate in a reversible way. And that's very important. When they aggregate, if you change temperature or concentration, they will be disaggregate. And that's very important because usually, as I told you, if you have the cosmetics, if it is too old, the colors aggregate, so you have oil in one part and dense part cooling the other. But even if you heat it up or cooling down, that's finished. That's irreversible. Here, that's reversible. So this is what we know about the stability of colloids. We used Stauber silica colloids, that kind of colloids of silica that grows in water. You can use also quartz particles or latex colloids, that's polymers. And these colloids, they are stable because the interparticle potential corresponds to van der Waals attraction. But to prevent sticking, there is a Coulombic repulsion. And this Coulombic repulsion makes the colloids to be apart. And they can be as a crystal if there is a minimum, or as a gas if there are no minimum.
Distance.
That's the distance between the particles.
Distance, but
yes.
why didn't you put figures?
Figures?
Figures.
Because it depends on, that's on the order of, that's nanometers. Okay, I don't put figures because that's the range, you see, the figure are the fact that's the range of van der Waals forces. The range of van der Waals forces, that's 100 nanometer. 100 nanometer. But I will give you more details later. So, that's figures. So, that's colloids, Stauber, 0.16 microns. And that's a mixture of water and lutidine. And in fact, that depends, you know that on silica, you have what we call the SiO-Si, silane bridges, SiO, and that's hydrophobic. You can have also OH radicals, and that's hydrophilic. In this Stauber, there are much more silane, silane bridges, So they are hydrophobic. And so that's what we got. So that's 26 degrees, that's 50 degrees, temperature, concentration. We will have figures later. Here, if you put the colloids well below the Beysens curve, they are stable. Now, if you are going this way or that way, that's different. If you are going inside this area, we have a reversible aggregation. And now, if we are in the coexistence, all the colloids will be in one phase, that is the lutein-rich phase, which is the lighter. They like lutein, so they go in they are hydrophobic. So now there's a difference in temperature. You see the difference in temperature between this and that temperature, with this temperature. And you see that depending on concentration, and this is the critical concentration, it increases and then decreases and go a little bit further from the critical concentration. So in terms of adsorption, you can see that this is the area of the critical adsorption, and this is the area of waiting phase transition. So this is another kind of experiment, which is by the Keller group. Directly was my postdoc, and that's water in polystyrene, and this is a surfactant, non-anionic surfactant with latex 0.26 micron diameter, and they get, this is the coexistence curve, and they get exactly the same, but they were very dense, so they get a crystal in the other phase. So this is quite general. So now, to measure what was the reason of this aggregation, we did light scattering experiments and making, say, two kinds of experiments. One in this area where there is aggregation, and the other in that area where there is no aggregation. And what we found was very interesting. So that's the graph. That's the silica colloids, and we observed that lutein-rich phase was sticking the silica colloids. So by chance, the lutein refractive index is the same as the silica refractive index. So if you assume that it corresponds to a layer of pure lutein, it is as if the silica colloids were growing from light scattering. And so we could measure easily the variation of the layer thickness here, log versus T coexistence curve minus T. And you see this is C plus, where there is no aggregation, and you see that it grows very much from a factor of 10. Now, we could measure also the critical concentration, we could measure the correlation length at this place and that place. You see that they become on the order when something happens. And that's on the other side where they flocculate or they aggregate. And you see they grow and they grow. It is larger at given temperature. They grow and suddenly there is aggregation. So it looks as for a large layer, the colloids are no more stable and they aggregate. And the value is on the order, you see, here that's the order of the correlation. Okay, now we can make another diagram. That's the thickness of the lutein layer versus concentration at different temperature. So that's far from the coexistence curve, and that's close. And you see that when you are going closer to the critical concentration, the layer decreases. And when you are going closer to the coexistence curve, it is increasing. Okay, so now we did something even better. That is, we tune the interparticle potential. You see that the repulsion of the colloids is due to Coulombic repulsion. So if you put the salt in solution, you will screen the Coulombic interaction and make the colloids to go closer or further or change. And that's exactly what's going on. So if this is a lutein layer thickness, that's in 10 minus 8 meters. This is T coexistence minus temperature, and this is what we put nitrate of magnesium, and this is the reference. There is no salt, so it increases when you go closer to the Beysens curve, and flocculate. Now, if you put some salt, this value, you decrease the layer, and you flocculate much closer to the Beysens curve. Now, if you increase again, you just put the adsorption upside down. Instead of having a little layer, you get a water layer. And you have no more flocculation. So this means that really this rutidine layer is a key parameter to understand the phenomenon. So that's another figure. Layer, TCx minus T. And that's details when we tune the salt. So we put some salt, and you see by increasing the salt, the flocculation is closer and closer. Okay, now something interesting. If you rescale the temperature not by the Beysens curve, by the flocculation, you get all the data follow the same curve. This means that the flocculation point is really something critical in terms of layer thickness. Okay, now another experiment, which is simple but also very pedagogic. You take water and you put in. So that's a sample, and you put water and rutidine, pure, no colloids, nothing. That's a picture. In fact, this was a program picture. It was on a video, so the quality is very bad. So, and you see, you can measure the contact angle. This means that water wets rutidine. Water wets the quartz wall. That's quartz wall. That's because here you have OH radicals, and that's the quartz is hydrophilic. That's fused quartz. Now, instead of pure water, we put water with silica, stubborn silica colloids. Because we thought it's strange that rutidine likes silica and not water. And now we wait about 1 or 2 weeks, and you see now it's exactly upside down. That is, water became hydrophilic with respect to the wall. That's because, here it was 2 phases, so there were all the spheres, all the silica bits came into the rutidine phase, and wets also the wall. So now the contact angle is with a carpet, a layer, a film of stubborn silica. So this really means, macroscopically, that rutidine wets the silica.
Why left pictures in not colors?
And because at that time, our video camera was black and white. But we can make false colors if you want. So what I did here, I put colors on it. Now, we look at the close-up. And that's temperature concentration of methylpyridine. That's 3-methylpyridine plus water plus heavy water. And you see that the flocculation, that's the 2-phase region, close loop. And you see that the flocculation curve goes all around. Because this corresponds to a critical layer of adsorption. And now, what we did was to change the concentration of water and heavy water to make the loop smaller and smaller. So the idea it is that reduce the loop and even having no more loops. Here it is. So that's a concentration that you have no more coexistence curve, just fluctuation here, but you see you have a flocculation. So that's really interesting. This is a system where we have no more phase separation of the bulk liquid, the 2 liquids, but only flocculation of the colloids, and where, by varying concentration and temperature, you can have either stable colloids or not stable colloids. So you can concentrate them if you want. If these colloids are proteins, you can concentrate them. That can be very interesting. So now remember that this was the temperature, concentration, and concentration of heavy water. So this is the coexistence surface that decreases. This is the aggregation surface. Here at the double critical point. So this here I showed you the aggregation curve with above and below flocculation region. And here, if you go closer and closer, we can make a double flocculation curve. So we didn't do that, but that's something interesting to see what is the criticality of this one. Now, what is the flocculation mechanism? You are tired? No? Me too? But that's nearly finished. But that's an important part. You see, that's interparticle potential that is called D'Alvio, Dariaghi, Landau, Verbeek, and I don't even know the last one. Landau, that's Overbeck, and this one, V, I don't remember. Dariaghi, Landau, okay. And so, depending on the economic attraction, you can have either a gas, and this is temperature below aggregation, or either a dense phase, crystal, and aggregation. So the idea is that when the lutidine layer forms, there are lutidine ions, and this change the interparticle economic repulsion and make the system either gas or liquid or dense like this. That's what this was my interpretation, version of my group. Other people have other interpretations. That's, for instance, people like Casimir effect, fluctuation. But that's very weak Casimir, very fluctuation on any of the critical point, and that's not exactly so. And also, that kind of capillary condensation, because it should be surface tension, and that's like a bridge. So that's another interpretation. Kind of bridge forming between the two columns. So we did some light scattering experiment. By doing light scattering experiment, we can get the structure factor of the system. So that's the intensity versus the wave vector. And so when you flocculate, you go from a Lorentzian to something which is different. So the intensity, increases, and the system goes near the smaller cube. So we can describe, and that's the line, we can describe the structure factor like the square of a Lorentzian. So that's the mass of the cluster, and that's the radius of the cluster. Why the square of a Lorentzian? Because here the slope is 4. Now if you put all the data with R and M, the slope is 4. Okay? So the easiest way to describe this curve is to make the square of a Lorentzian. And it works well. Now, with time, with time, the evolution is well fitted by making the radius growing as t at the power 1/3, and that's a diffusion limited growth. That is, the colloids, they diffuse by a Brownian motion, they have their layer, and they stick, and that's diffusion limited growth. And at the same time, that dense cluster, because the mass, here the mass varies as r to the power 3, that is, and is proportional to t. And that's exactly, if you see the mass, that's the intensity, and the radius of the power 3, you see that with time is proportional. And you get the power 4. So we can describe the process of flocculation. And the most simple vision of the clusters that you have small cluster aggregating together like this by Brownian motion. And the problem is, do we have a real surface tension or not between the clusters? We have a concentration gradient, so we should have a surface tension. And that's why we have a -4 power. Now we studied also the defragmentation process. Very interesting, but I think that's out of the scope of the lecture. And so I will just finish it up now. And so concluding on that, the reversible aggregation of colloids that we have observed is a general phenomenon. And it should have application in biology, and that's the color group in Philadelphia that is working with it. The models, they are still in competition. We propose that the LVO is tuned by one layer forming. Some other propose Casimir, the fluctuation, and some other, as the Yeoman's group in Oxford, they propose a surface tension phenomenon. So, more is needed. So I'm nearly finished, but I would like to show you something and to thank you, because it happened something very strange, very important to me yesterday. You see? That there is So I wanted to tell you that's a new experiment for me. Okay, now if you have questions. So.
Вопросы можно на русском задавать, если хотите. Можно на английском? Сережа, у вас есть вопросы?
Show pictures about Casimir effect and explain it again. Casimir effect.
The Casimir effect, in fact, that you know, the Casimir effect is based on the fact that if you have fluctuation, from the fluctuation can occur, attraction. If you have fluctuation between two walls or two colloids, the fact that there are fluctuations make these two walls attract. So there was some people telling, and that's wrong, now we know that's wrong. You see, if you have, for instance, two boats on the sea, and the boats, they are close together, and they are waves of fluctuation, so they attract to each other. But that's not so. And so if you are...
The interaction between two bodies.
Two bodies, yes. Two bodies. It's like Van der Waals, but people can explain Van der Waals by Casimir. Because the Van der Waals forces, they come from fluctuation, either. The basis of the...
From what time is the name?
Casimir, I think it was also maybe somebody knows better than I know. I think it was a Belgian physicist. So the time of Plato, I guess, from the 200 years ago, I think 19th century. But you know, I don't have my computer, but maybe Casimir effect, Wikipedia. And you have a lot of wrong. That's the problem is with Wikipedia, you have to know. If you don't know, you can get mistakes. Especially with Casimir, you know, there are strong groups in Germany. They call Casimir something that is not Casimir. Since they are good old friends, I cannot tell them this way, but you know.
Not physicist.
No, but many people have told about Casimir. That's the group by Dietrich. Dietrich. I can't give you the reference. I don't have a reference. That's Dietrich. Okay, so. But I can tell you that's not so difficult experiment to be done. A number of these experiments have been done with collaboration. But this collaboration with in Bangalore in India with Anil Kumar Anil Kumar was an expert of closed loop system, and so we did an interesting experiment with him. And the equipment in the lab is not so big. You need temperature regulation. Wow, not so much. 0.1 degrees, you know. And colloids are easy to manufacture by yourself. You can buy also. And oh, but he is looking at me with a video camera. So, oh la la. So I shouldn't have shown my Permiac picture.
Вопросы, пожалуйста.
You said that your result is useful for biology, and so for medical science.
It could be. I say it could be.
Maybe something else.
Maybe?
Maybe in something else.
Something else, yes. If you want to concentrate something, that's easy to do, you know. That's something we looked at. There is I know that there is a renewal of interest for this phenomenon. And I am a person with whom I collaborate. He said that he is in the United States, and the group in which he is studying also this, and also this theorist in Japan. For me, I stopped doing experiment at the beginning of 2000, it is 10, 12 years ago, because for me, everything could be interpreted in terms of the LVO potential modified. So now I'm also a former postdoc. He was the student of Anil Kumar in Bangalore. Now he's working, he has a permanent position at Grenoble, at the ESRF, European Sector-Evaluation Facility. So he can study the colloids with X-ray, so looking at more precise details than with light scattering. And so he's also much interested in this kind of thing.
About right pictures, it is difficult to receive this function.
No, you can calculate this function. If you know the concentration of ions, etc., you can calculate. The van der Waals you can calculate. The van der Waals attraction, you can calculate from the refractive index of the material, for instance. And also there are some infrared and UV bands. So this you can give the amplitude of van der Waals forces. The Coulombic repulsion you can get from the ions in solution and the charge that you have on the silica. We did it. We made a model where we can have this variation and we can reproduce the flocculation line with not so bad accuracy. We published it in 98, I think. I think this is this paper. I'm sure that this paper is somewhere. Yes. Here it is. And that's this paper. That's in honor of John Cam. So that's a special issue. John and Statistical Physics. So this paper, if you look at it, you can see all the details of the calculation of the DLVO potential, and we could reproduce the flocculation line.
Are you able to change the parameter of DLVO potential in your experiments?
Why?
For instance, you make a comparison between your results and DLVO theory, between experiments and DLVO theory. Next, maybe it's better to change the pair of the liquid, to change the Delvaux potential parameters and.
But this has been done. This has been done by my group and by other groups.
Okay.
Yes, that's.
So now there is no any competition between different effects.
Theory?
If your experiments are confirmed by your theory.
The problem is that there were experiments also by the Dietrich group, that very good experiment. But the problem is that the same experiment can be interpreted by different theories. You know. Because it's, well, you know, the problem is whether the increase of the lutein of one layer is due to the fact of the LVO change, or the LVO change because there is an increase of the layer. You know, that's the egg and the chicken, you know. Who is the egg? Who is the chicken? But that's... I would be pleased if people are interested in doing some other theory or experiment to collaborate with. Of course.
Денис, у вас есть вопрос? Так, у кого еще вопрос? Русский можно?
Все-таки вода у него лилок.
You know, the salt is very important in Pearl.
Ah, you.
From the very beginning. So you should look very carefully with salt and water and something else.
Гриша, у вас нет вопросов?
I don't know any group or person working in this area. I don't. Maybe there are, but I don't know them. That's, I know. You know the groups that I know. That's the people in Germany. I know well these people. There was also groups in a very strong group with Lecция in Netherlands, but they were not doing exactly this kind of experiment. They were doing more general experiments and theory with colloids. And one of I am a student from there, from doing the belt. And there was also a group now in another Ville students, and there were groups in Pittsburgh, Chimie, but now they are not working anymore in this field. Humans, I think, they stopped doing theory. That's a technical group in Oxford. The only group that is currently working, that's a Dietrich group in Germany.
Есть вопросы еще?